Day 4 of 365 was the first day where complexity analysis started feeling close to real code review instead of theory. Big O, time complexity, and space complexity are useful, but they stay abstract until I can look at a loop structure and estimate what kind of growth it creates. The useful shift today was stopping the mechanical loop count and starting to ask how the work actually accumulates through the code. The first big lesson was that a single loop usually suggests linear work, but that is only true if each iteration does constant work. If the body of the loop hides another expensive operation, then the surface shape can be misleading. That matters because a lot of interview code looks simple at first glance. The real cost is often buried in what each iteration is doing, not in the number of loop headers I can see. Another useful shift was learning not to panic every time I see nested loops. Two loops over the same input often do mean quadratic growth, and that is a real warning sign. But not every nested structure explodes in the same way. Sometimes the inner work is bounded. Sometimes two pointers only move forward overall. Sometimes the total number of steps still adds up to linear behavior. That means I need to analyze how the indices move, not just how the loops are indented. That also made consecutive loops much clearer. Two separate passes over the same array usually add together and stay linear. They do not automatically multiply into quadratic work. That sounds basic, but it is a common analysis mistake early on. Once I started separating nested costs from consecutive costs, the dominant term idea became much more concrete. Another big lesson was that recursion is still loop analysis in disguise. A recursive function is also repeated work. The only difference is that the repetition is spread across call frames instead of written as an explicit for or while loop. If each recursive call reduces the problem by 1, the growth may be linear. If the problem is split in half, the growth might look logarithmic or n log n depending on the work done at each level. The most interesting new idea today was amortized analysis. Some operations look expensive if I isolate a single step, but they are cheap on average over a long sequence. Dynamic array append is the classic example. Most appends are constant time. Occasionally, the array resizes and copying happens, which is expensive. But that expensive resize is rare enough that the average append cost still stays 1 amortized. That changes how I should judge a sequence of operations. That is important because pure worst-case thinking can sometimes be too pessimistic. I still want to know the worst single step, but I also want to know whether the cost is rare enough that the long-run behavior stays cheap. That is exactly what amortized analysis captures, and it makes data structure behavior much easier to reason about honestly. Another useful shift was focusing on the dominant accumulation of work. Do costs add? Do they multiply? Do they shrink recursively? Do they spike occasionally and then average out? Those questions are much more powerful than simply counting visible loops. Once I started using that mental model, the code felt easier to classify before I even wrote down the final complexity label. This matters outside interviews too. A performance bug in production often comes from misunderstanding how work accumulates. Maybe a harmless-looking nested scan landed on a hot path. Maybe a resize-heavy data structure is still fine because the average behavior is acceptable. Maybe a recursive walk is using more time or stack depth than expected. Loop analysis is one of the fastest ways to catch those issues early. So my main takeaway from day 4 was that loop analysis should become a habit of tracking how work accumulates, not a habit of counting syntax. Ask whether the costs add, multiply, shrink, or amortize. Ask what the loop body really does. Ask how recursion is changing the problem size. If those questions become automatic, later DSA topics get much easier to judge. That is what made today useful. Complexity analysis finally started to feel like reading real solutions.